Yeah, welcome back again. Like I said earlier, we have talked about the binary compounds and we want to look into the tertiary and the quaternary. So we are bringing tertiary and quaternary together because they form a bulk of the compounds that we name. So among them we have acids, we have salts, we have complex compounds that we are going to be looking into. Now, when we talk about the first category, the oxo acids, they are acids containing oxygen. And I know some of you will be wondering, are there acids which do not contain oxygen? Yes, we have. Hydrogen chloride or hydrochloric acid does not contain oxygen. Yes. So it's not an oxo acid, but yet it is an acid. Now, when we want to name oxo acid, the first thing you do is that you name the oxygen first, but the oxygen is preceded by the number of its atoms. So the number of oxygen atoms comes first, followed by oxygen named as oxo. Now, the Greek prefixes are used in numbering here. Mono for one, two for di for two, tri for three, tetra four, and so on. So in cases like this now, we say we name oxygen first as oxo. Then we go to the central element in the compound. We modify the name of the central atom to end with 8, ATE, and its oxidation number, designated by Roman numerals in brackets, is also indicated. So, like I mentioned earlier, your knowledge of oxidation number is very, very important. If you are forgotten, you can pick up your notes and revisit it. So, now, in ending, you add the word acid to the compound to make up for the name. Now, what we would do when we name oxo acids is that we don't name the hydrogen that starts the compound. Instead of the hydrogen, we name at the ending acid to each of the name. And once you see acid in any compound, the first thing expected of you to know is that the first element there is going to be hydrogen atom. Now, the few examples we have HNO3, HNO2 first. Now, we said oxygen is named as oxo, but in this case, you are having two oxygen atoms, which is di. Di. The Greek of two is di. So we say that is dioxo. Now, the central element here is nitrogen. Now, if we modify nitrogen to end with 8, it gives us nitrate. So that is dioxonitrate. Now, in determining the oxidation state, your hydrogen is plus 1. Then you have the oxidation state of nitrogen to determine. Then oxygen follows. There are two atoms of oxygen there. Each oxygen atom is having oxidation state of -2. Everything there adds up to 0 because it is a neutral compound or a neutral compound, yes. So in calculating, you have plus 1 plus n minus 4 to equals 0, and that would be n minus 3 equals 0, such that your n would be equal to plus 3. So if n is equal to plus 3, so we said the oxidation state of nitrogen there is 3. So we say di for 2, oxo for oxygen, nitrate for nitrogen. The oxidation state of nitrogen there is 3, so we say oxonitrate 3. So to end it or to cap it up, we call it acid. So that gives us dioxonitrate 3 acid. So the next compound is HNO3. If you calculate the oxidation state of nitrogen in HNO3, it should give you 5, just like I have done above. So 3 there is tri. Say that is trioxo. Then you have nitrate for the nitrogen, 5 acid. The same thing applied to your H2CO3. Carbon being the central element there, you call that carbonate. Then for H2SO3, that is a mistake. So instead of being carbonate there, you have sulfur as the central atom. So you call that what? Sulfate for sulfur. So that is trioxo for O3 that ends the compound. Sulfate for S. Then the oxidation state of sulfur there is going to give us +4. Then you end it with acid. That is in the case of the oxo acid. On your own, you can just give a trial to H3PO4 and some other compounds like H2SO4 is another acid you can find a name to. You also have HiO4. The I there is representing iodine. So just try and find names to them as you go on with the class. That will help you to know if you have actually cracked the naming of oxo acids. In that case, we move on to normal and acid salts. Normal and acid salts. Now, but before I go on to that, I want to bring something to our notice. There are such things that we call acid radicals. Now, if we take off the hydrogen from HNO2, it will give us NO2 minus. As in NO2 minus. Now, this is the acid radical for HNO2. A case whereby you are going to need the name of this particular radical, what do you do? How do you go about it? All you just do is remove the acid at the back of the name of the acid and replace with ion. So for NO2 minus now, that will give you dioxo nitrate 3 ion. Simple. So in a case like this, when you have HNO3 minus for this, this is going to be NO3 minus. Try finding out the name. In the case of this one, you'll be having CO3 2 minus. I know you'll be wondering why are some minus and some 2 minus. You can reflect back to formation of compounds that we looked into earlier. How come? If one is H2 H plus and you're having CO3 2 minus, the compound form is actually going to be that. So let's move on to what we said, normal and acid salts. Now, a salt can be defined as a substance formed when the replaceable hydrogen atoms in an acid are partially or completely replaced by a metal or ammonium ion to give an acid salt or a normal salt respectively. Now, what do we mean by saying that? If this is an acid, let's take H2SO4 for example, being an acid. Now, you're having 2 hydrogen atoms. You can replace one of the hydrogen atom there with sodium. So that should give you NaHSO4. Or you replace the two hydrogen atoms with a metal to give Na, sorry for that, to give Na2SO4. Now, a case where you replaced with one and you are still having a hydrogen atom in the compound, that one is an acid salt. But a case where you replaced completely to give you Na2, in that case, what you are having is a normal salt. So, just like the way we named an acid, their names are ending with acid. But in this case, we are naming salts. So names do not end with acid here. What you just do is that you name the cation first, which is the first element that precedes. Then you follow it up with um, the anion or the acid radical that you have, which is the last part of the compound, is what ends it. So when you are having compounds that are having variable oxidation states, like you're having copper, iron, the ones we mentioned, group 4, 5, 6, 7, and the transition elements with the exemption of scandium and zinc, which are 21 and 30 respectively. So those ones do not have. But other ones between 22 and 29 have variable oxidation states. So you indicate their oxidation numbers. So the names now: potassium trioxonitrate 5, as in KNO3. So K is for potassium, N is for the nitrate. So like we mentioned there, you want to name NO3. You name oxygen first as oxo, indicate the number with tri. Then the nitrogen, which is the central, is named as nitrate, which is oxidation number indicated in brackets. So for CuSO4, you have copper 2 tetraoxosulfate 6, ammonium tetraoxosulfate 4 for NH42SO4. Then you have NaHCO3, CaHSO32 for calcium hydrogen trioxosulfate 4. Then K2Cr2O7, potassium heptaoxo dichromate 6. To calculate oxidation number of chromium there, it should give you 6, as the case may be. Now, when we come to hydrates, because I'll be taking a break on hydrate for this recording, so that I can come back to bamboozle you with that of complexes. Now, hydrates, all you just do is indicate the number of water molecules having named the salts. So you have sodium trioxocarbonate 4, and you're having 10H2O accompanying it. So that is the 10 there is deca. And whenever we are naming water, water is named as hydrates. So that is decahydrate. You have iron 2 tetraoxosulfate 6 heptahydrate, and you have cobalt 2 chloride monohydrate, simply because it contains only one water molecule. All right, let me take a break here because I'm using my blood too, and my sweat and my energy. So I'm taking a break here, and you will see me again, or hear me again, or possibly I would like you to see me again. So you see Mr. Fire me again in the next video. Thank you.